So, before we get started, a couple things I want to mention. So I think I mentioned this. It's been after last class. So I updated problem set 5. There was a kind of a small typo on one of the problems. I kind of changed it just to be a little bit more clear. So if you're working off an old Word document there, make sure you're looking at the new Word document. All the data is fine. It's just kind of, there was a one question where I kind of altered the language. So if we're thinking about kind of where we're at, that last quiz, that due date has passed, so we're gonna have that quiz in there. I said the next thing that we'll have, that problem set 4 was due last Friday. So I started grading that this morning when I have my graduate assistant. I'm kind of teaching them how to kind of approach assignments like this. So they're kind of helping me with that grading. So you should see these grades start to pop up over the course of the week. They likely should all be completed by the end of the day Sunday. I'm hoping by the end of the day Friday. My graduate assistant's a little busy, and so I want her to kind of have some practice with some of these. So it might not be until the end of the day Sunday. But I'll get this posted, the answer key quiz to problem set 4, so that if you want to start reviewing it even prior to it being completely graded, you can kind of start to do that. So there was the one problem where I said I was going to give everybody full credit for, so you can kind of review questions like that. So I'll have like a do file, but then also kind of the answer key up there, what the answer should have been. The next thing that we currently have is that 5th problem set. So I don't have that set to be due until the 19th, would be next Wednesday, end of the day. So you still got more than a week to work on that. It is purely related to what we talked about with interaction terms. So it's only interaction terms. Excuse me. However, what I'll be posting possibly after class today, depending on how quickly we move through material, but definitely after class on Thursday, will be the next quiz, right? So that quiz I'll have set to be due the end of the week next Friday. So it's going to be due after that problem set. Now, the sample questions are already up there. Some of them might look a little bit confusing because we haven't talked about the data issues. So the majority of that quiz will also be related to interaction terms. There's going to be a couple questions, like you see in the problem set, where it's related to what we're going to be talking about this week, which is data issues. So we'll link a lot of this data issue stuff to things we've already talked about. So as you look at those practice problems, even some of the stuff we haven't covered might make a little bit of sense, but after this week, you should be able to answer every single question in those sample questions for number 5. Those will be kind of the questions you want to review before taking quiz 5, which, like I said, likely I don't think we're going to get through all the material today. So that will probably be posted after class on Thursday and due at the end of the day next Friday. Okay. So that's kind of where we're at with the class. Any questions for me before we dive into material here? Okay. All right. So we've kind of got our PowerPoint slides. We'll start with those. We'll also start working with this data issues F25 do file. That'll be the kind of first file we look at. Might dip into this Monte Carlo file today. If not, for sure, we're going to go through that on Thursday. So let's get these pulled open. We'll start to think about what we were talking about with nonlinear terms, whether this was including a squared or a cube term, log relationships, interaction terms, was basically identifying the right specification, right? We know that this simple linear regression model that we had likely isn't going to capture everything, right? And so because if we don't include interaction terms or nonlinear stuff, we might have limited variable bias. Because of that, we want to identify the correct specification. We're going to deal with more of what I would call kind of data issues, which encompasses a wide variety of topics. So this is going to be a little bit more variance in the topics we discuss for this week / module, if you want to think about it that way. So the first thing is relatively, I would say, easy compared to what we're going to do. I've got some examples to kind of go along with this, but look at regression results. We want to be concerned about the validity of our results. So what we're ultimately trying to do, we'd be coming up with predictions, calculating marginal effects. But when we make these statements, we need to make sure that our data, we're not making statements that are too broad, right? And that we are only making statements of what our data will actually support. Okay? So the idea of internal and external validity is going to be whether or not we're accurately identifying the causal relationship or the cause and effect between this X variable, our right-hand side independent variable, and its impact on our Y or a dependent variable. So internal validity That's going to deal with things like omitted variable bias, that we're making sure we're accurately capturing this cause and effect. Right? We don't have omitted variable bias existing, not predicting a linear model when it should be quadratic, right, et cetera, et cetera. Now, external validity is when we have a data set, we need to make sure we're not taking, even if we've eliminated any of the internal validity concerns, we make sure we've got the right model specification, we've got no omitted variables. We need to make sure that I'm not using, for example, a data set on the labor market for, I don't know, computer scientists, and trying to take that information and making statements about the labor market for, I don't know, crane operators. Because those two labor markets are very different. Our results from data scientists in terms of the labor market might not be applicable to other labor markets, right? So a lot of the times what you'll see in economics is we want to try to get a question answered with our data where we can make as broad a statements as possible. If I can understand the way that this labor market works, right? Hopefully I've done so using a data set that makes the results applicable to many other labor markets as well. But if there's some things about the labor market for data scientists that are very specific and they don't apply to a lot of other labor markets, well, my results, I can really only speak to the labor market for data scientists, right? That's the idea of external validity. I want to make sure if I have external validity, I can use my results to make statements about other types of labor markets, just in my example. This could be also at the firm level. I'm looking at the firms of one specific industry. I want to be able to identify a cause and effect relationship, maybe between, I don't know, output decisions and marginal costs that would apply to a variety of different industries. Or I want to make sure my results have external validity, validity outside of just the specific data set I'm looking at. So we want our results to be able to be generalized. Sometimes this won't be the case. We kind of see a lot of the topics that we're going to talk about this week, we're handheld by the data. Right? Sometimes there are no way to solve the issues that we run into. So for example, I don't know, if I'm looking at like a data set where I've got hours studied and performance on high school tests, well, maybe that's going to look very different than the effect of hours studied on a college exam, right? In fact, I have this discussion with a lot of my students, especially freshmen. They're used to high school where if I put in X number of hours, I'm likely going to get A or B, right? Because a lot more of it's rote memorization, learn these rules, whereas at the college level, things start to become a little bit more conceptual, right? And so hours studied, simply putting in more time doesn't always equate to an extreme improvement in my exam performance. My results from my high school students will not be it's a hard one for me. Generalizable, there we go, to college students, right? So I need to make sure that I have some of this external validity, and sometimes I won't. And I just can't make any statements about the effect of hours studied for college students on their exam performance, right? I can only speak to the impact of hours studied specifically for high school students, if that's my data set. So some threats to kind of this external validity that will kind of pop up quite often is maybe I just have differences in populations, right? So maybe the data set that I have, for example, if I want to know the impact of gender on wages in Namibia versus the United States, I have two very different populations. If I run this very simple linear regression trying to predict wages using this dummy variable of gender, it's going to look very different for its impacts in Namibia versus the United States. I'm not going to have external validity there. Now, I might also have just a difference in settings. So maybe I'm looking at kind of a similar population, right? I'm looking at all college students in Indiana. But if I want to know the impact of ad campaigns on alcohol consumption at IU versus BYU, so this is Brigham Young, if you're not aware, it's a Mormon institution, those impacts are going to be pretty different, right? And so even though I have the same population that I'm sampling from, college students in the United States, if I've got different settings, that potentially is a threat to my external validity as well. So what we'll ultimately end up with is a lot of the times we can really only speak to a very specific causal effect relationship for whatever our data set is looking at, whatever population and setting our data is looking at. If we try to extend it outside of that, we're likely going to run into external validity concerns, okay? So another example that we would have, a simple way of thinking about this, here I got to make sure I have it set to my desktop, so we'll go to File, Open. I've got data set I'm looking at here. I think life expectancy. Let me make sure for the remainder of today's class. I've got my global path set correct. I'm going to open that life expectancy data. And first thing I'm going to do, it's as simple as thinking about this, right? I want to know the impact of GDP on BMI, right? Maybe that looks very different in a country that's considered developed versus a country that's considered developing, right? In developed countries, typically food is not the scarcest of resources, right? And so if I run these regressions, essentially just using a conditional statement, while I'm only running this regression for developed countries versus ones that are considered still developing, I have two very different settings or two very different populations. I'm going to have very different results, right? So if I run these two regressions, notice my coefficient from the developed countries is negative 0.0025, highly statistically significant, right? P-value is 0.003. For those developing countries, I get a coefficient that, although not quite statistically significant, very close, but notice it's the exact opposite sign. So I not only will see size differences in that coefficient if I'm looking at a different population, I could see completely different signs on that coefficient. So this is would be the idea if I'm using results from only developed countries to make statements about developing countries, I'm going to end up making really poor decisions, right? And so just to kind of get some practice, I think this is like an easier concept, this idea of external validity. How would we start to interpret these coefficient results, right? Just kind of rehashing some old things we've talked about. But what type of model am I running here? Got the natural log of BMI and the natural log of GDP. So I've got a log. So everything should be in terms of what? When we take the natural log, we've essentially, I said one easy way to think about this, the units are now percentages, right? So if everything is in terms of natural logs, I don't have to make any conversions. So my interpretation of that coefficient is going to be if GDP goes up by 1%, the expected BMI in that country is going to go down by what? 0.0025%. There's no moving of the decimal. Everything is in terms of percentages. If we had a linear log or a log linear, that's where we start to have to either divide or multiply by 100. If everything's in terms of logs, everything remains as is. That is the coefficient. It's just the interpretation. Everything is in terms of percent changes. So I can kind of think about here in a weird way, what's the elasticity of BMI in respect to GDP, right? Well, it's inelastic, it's less than 1, right? But also that as GDP goes up, I see that in these developed countries, that tends to be that BMI goes down. The more resources we have, maybe if they're concerned about food, they start to be concerned about having too much food, right? And being too overweight. Now, if I'm looking at developing countries, we have a similar kind of interpretation, but now my coefficient is 0.0015. So now every 1% increase in GDP would actually increase the BMI in developing countries by 0.0015%. We get the exact opposite effect. And we're still looking at developing countries, their increases in GDP, well, now people have more money, maybe food is more of a scarce resource, they actually will see that the average BMI in those countries is going to increase, right? Two very different settings, we get two different effects, okay? Even if I had a bunch of controls, no omitted variable bias concern, I've identified the correct specification, maybe the log was the correct specification, I've eliminated internal validity concerns, I still have to worry about the fact that I have different settings or different populations here. So that's as simple as because of what threats to external validity would be. And you could do a very similar thing if I'm looking at the effects of GDP on population. So just before I kind of go too far into this, like, let's just think about before we look at these results. In developed countries, right, this is where this is an applied econometrics course. We want to start to think about what relationships we're identifying. If people have more money, this is this kind of increase in GDP, we can think about it as income, right? There's more wealth in these countries. For developed countries like the United States, as people have more money, you may not know this, I guess, ahead of time, but if you were to kind of go out and do some quick Google searches, what's happening as our GDP grows? The number of children people are having goes going down. But what's going to be happening in developed countries, typically as GDP is going up, people are more concerned about things or maybe providing more resources to a single child as opposed to multiple. So I might expect that GDP going up is actually going to cause my population to go down. Okay? So if I looked at these developed countries, okay, well, not quite, right? It goes against kind of what we typically see, but this is not just the United States, this is every country, right? But as GDP goes up, I'm actually seeing that my population is also going up. Now, also, I'm not looking at birth rates here. So having a higher GDP is one way I can get a higher GDP if I simply have more people, right? So there's that relationship going on as well. Now, if I were to look at this result and say, okay, for every 1% increase in GDP, I can expect the population of a country goes up by about 0.81. Well, that's only if I'm looking at developed nations. If I look at developing nations, there I see the same sign on that effect, right? But what is the increase in population for those countries? Not quite as large, right? I mean, very close, right? Very similar. So here I might not be as concerned with threats to external validity because I'm getting a very similar coefficient, right? Now, there's still going to be a difference, right? Because I'm looking at two different settings, but at least here we don't see like a vast difference in those two coefficients. So maybe here, this relationship between GDP and population, I'm less concerned with making statements if I only have developed countries because I'm seeing pretty similar results for the developing countries as well. So here I'd be less concerned about external validity concerns. Any questions on kind of this idea? Like, once again, just introducing the idea of data issues where we start to think a little bit harder about the data sets we're using and the statements we're making. Okay. So the internal validity, we really have already talked about these. I kind of mentioned them already, but basically, are we getting an unbiased estimate? So this is going to be more related to things like, do we have omitted variables? Do we have a functional form misspecification? We've really kind of already talked through these things, right? There's tools we have to solve internal validity. We can go out and gather more data to get additional controls. We can try running multiple models. Which model, if I have the same dependent variable, what's going to be a really good identifier in most cases that the model is preferred? A higher. So I can look at the statistical significance of my X variable, but no matter what I'm looking at, if I'm looking at natural log, quadratics, what's one statistic I can compare across any of those as long as the dependent variable is the same? Adjusted R squared, right? And I want that adjusted R squared to be higher if the model is preferred. So we haven't really talked about ways of kind of solving. We didn't dive too deep into it. But we also had like heteroscedasticity. That was where I think going back a ways, we use like the robust command, right, to kind of control for that. Those are all things that are going to influence the kind of whether or not our coefficient is unbiased and whether or not we're getting the correct p-values. Okay? So, you know, I don't know. This is kind of a catch-all. We won't talk a lot about these things yet. But basically, if I have internal validity concerns, like I have omitted variables, what can I do? Well, you know, the easiest way we talked about, I can first think about if there are other data sets that exist out there. We could start to put a sign and a size to what the bias is. So these are things we've already talked about. I can go out and get more data on those additional variables I want to include as controls. I can also just think about, even if I don't have the data, what are some omitted variables that might exist, right? So if I think, for example, I was talking with someone about the choice of taking, I'm still getting used to numbers, 370 as a prerequisite versus Math 2 something. Some of you might know, I don't know. There's two stats courses that are kind of interchangeable. One's in the math department. Well, if one of those is considered an easier course, what's going to be true? We're going to have students who are more likely to take that course are likely students who have lower statistical or lower GPAs, lower like math skills. And so there I might think that there's a bias that exists if I'm looking at like a dummy variable for taking the math versus the econ statistics course, right? I don't have the actual data, but I can think about what would the sign of that bias be? So I might not be able to solve it, but I can at least think about, is that coefficient I'm seeing, what's the kind of bias that exists? That's about as far as we kind of pushed it. We'll eventually start to talk about things like panel data issues, use of instrumental variables, economic experiments is another way that we can kind of solve internal validity concerns, but we haven't quite got there yet. All right, so we'll kind of revisit these internal validity concerns really after this week. because we will talk about instrumental variables and we will talk about the use of panel data. So this is kind of like a foreshadowing things to come, right? And then I don't want to kind of spend a whole lot of time on this because we've really already talked through functional form concerns with internal validity. We just said which one do we want to choose, the one with the highest adjusted R squared. We haven't really kind of went through probit and logit regressions. We're not going to really dive into that in this class, but if you took the next level of statistics, we would start to think about not only can we estimate relationships with squared terms, not only can we estimate these kind of natural log or log linear models, we have slightly different specifications we can use when I had a 1-0 variable. What's an issue that we ran into when I wanted to look at the different specifications? So if I wanted to run a log linear, but my dependent variable was a dummy variable, why can't I do that? I can't take the natural log of 0. So we have two other forms of regression that we can use when we have dummy or categorical variables that have 0 values, which are probit and logit. That would be kind of the next level of statistics, another way that we would have to kind of solve this issue. We're not going to dive into that in this class. What we are going to dive into here today is what if we have measurement error? So this is one thing we haven't talked about yet that we are going to talk about. So let's say I gather this data, but I believe that it's been incorrectly measured. Okay? That for whatever reason, the data that I'm seeing in my data set has been, a couple different ways. We can think that either it has been entered incorrectly, right? There's just been some errors that people are making just by the fact that data entry, there can be errors. Or maybe that there was, what word am I looking for? Intentional errors made. Maybe companies were overinflating their reported revenues, right? Or maybe certain students are over kind of estimating their actual hours studied, right? When they report them to you. And so there we're going to have data that actually is incorrect. It's not the actual value, it was the self-reported hours studied. It wasn't the actual hours studied of the student, it was self-reported. Or it wasn't the actual revenue of the firm, it was the self-reported value that they gave to whatever this company was, or this overseer was. So a lot of times they'll pop up with survey data, right? So I've worked with some survey data before, and like a real popular one is like time use. So hours studied is one. Like, what do you think most people, if I ask them how many hours they studied for an exam, most people are probably likely going to do what? Self-report higher or lower number of hours than they actually studied. They're probably higher, right? Even if they don't do it on purpose, it feels like I studied for 20 hours. Maybe I only studied for 16. And maybe I'm not off by that much, but I'm still not giving exactly the correct value. Or if I ask about alcohol consumption, what do you think happens to survey data when you ask people under 21 what their alcohol consumption is? The mean tends to be a lot lower, right? If I'm worried about anyone looking at this data and potential, down the road implication, I might underreport, or I might just put a value of 0. I'm intentionally going to lie. So we can kind of think about when we're running these regressions, we're not actually using kind of the X value. We're using this self-reported X value, okay? So the self-reported value will be, right? So if I think about what I'm doing here, what do I want? So I've got, when I'm running kind of X, actually, this is what I want. Yeah, so all I'm doing here is thinking about when I run my regression, this is the self-reported value. This is the actual data I'm using. So what ends up happening is the true error term, right? When we run these regressions, we said we could actually come up with a predicted Y value and then take the difference between the predicted and actual Y. That was our error term. Well, if I have misreporting in the data, when I run the regression, I won't actually have the correct error term. My error term will be whatever the error would have been, plus the measurement error that existed in the misreporting of this data. So I can kind of think about it as, yes, I can use the self-reported data, but my error term now, that difference between my actual Y and my predicted Y values, is going to be much larger than it was before, or people tend to under or over report, it would kind of change whether or not the error is small or large. It changes the size of the error. So what that's going to do is it's going to screw with our statistical significance. Okay. So let's think about why. If we go way, way back to the simple linear regressions, one of the assumptions we had was that the expected value of the error term, what we're coming up with, this line of best fit. So if the data looks something like this, when we came up with our line of best fit to make our predictions for y using different values of x, the expected value of our error term at any x value we said needs to be 0. This was the problem when we tried to estimate something if the data instead was not linear, and I try to estimate a linear relationship. We said, okay, at some values, most of my errors are positive, and at different values for x, most of my errors are negative. We had the issue that our expected value of our error term wasn't 0 anymore. The same thing exists if I try to run this regression, but I'm using data where there's misreporting or measurement error. Right? The expected value of my error might not be 0, right? Because if I'm looking at people who drink more often tend to be ones who underreport how much they drink. Well, now my coefficient, my expected value of the error for all those individuals at the higher end of alcohol consumption, my predictions are always going to be way too low. The expected value of my error will no longer be 0. So that's kind of the idea, or kind of what our regressions are going to fall victim to when I have misreported data, or essentially measurement error in my data. Okay. So what can we do, right? So we'll kind of do a kind of quick little trick. I'm not going to make you do this math every single time. We just care about getting from point A to point B. I'll show you why, and then we'll kind of use point B to kind of deal with this issue of measurement error. So let's say I have some measurement error such that the actual x values are going to be whatever the self-reported value was minus that error term. Okay. So when I'm looking at the actual data, what I see is x tilde. That's the self-reported value. The actual value will be whatever that self-reported value is minus the error term. Now, this error term could be positive or negative. If it's negative, then x, the reported amount, would be lower than the actual amount, and vice versa. But we're just going to rewrite it. The actual x value is the self-reported value minus that measurement error. Just rewriting this. Okay. I haven't changed anything about the equality of this equation. I'm then going to rearrange things a little bit. So if I'm using the self-reported data, here's the coefficient I would see. Okay. Well, what happens to this? I don't have data on the measurement error. That's like, Bill, I can't see that. So what ends up happening is that ends up in my error term. So now my error term includes the original error that would have existed in my predictions plus this measurement error. So U is just going to be, you can think of it as like our new error that includes the measurement error. Well, what's going to be true, right, if we run this regression, is that the coefficient estimate on the self-reported data will have a bias in it, right? Because if we had an important omitted variable, what did the bias in our estimate become? So we said before, when we look at these estimates, if we have an omitted variable that is related to the x variable we included, the bias would be the effect of that omitted variable times the covariance of the variable we included, the variable that was omitted, divided by the variance of the variable we included. Essentially, measurement error is just an omitted variable. We don't have data on it. It's not actually getting put into our regression. And so we can think of it as though it's an omitted variable. Right? So I'm going to have a very similar kind of bias that exists if I have an important omitted variable, which is the measurement error. Okay? Now, we can simplify this a little bit because ultimately, what is that measurement error going to be? It's going to be the covariance of the self-reported data with negative whatever the actual coefficient is, multiplied by the error term. This was the omitted variable, right? This entire thing was the omitted variable. So that coefficient, that covariance between the self-reported data and our error term, we know now that's not going to be 0, right? Because we have this important omitted variable. So if we kind of rewrite this and divide it by the variance of the variable we included, which is the self-reported data. Well, the covariance of the self-reported data with the measurement error, if the way in which self-reporting the measurement error exists is in any way related to the actual X value. So if my alcohol consumption that I report is in any way, I'm lying or I'm misreporting it as a function of what my actual alcohol consumption is, then this covariance is going to be something other than 0. So this covariance would be something other than kind of 0 here. Now, the original error term, right, that doesn't include the measurement error, the covariance of our observation with that error should still be 0. So that kind of goes away, right? So we're left with just the covariance between the self-reported value, which is the actual X value plus the measurement error, and then the covariance of that with negative beta 1 times the measurement error, right? Because the covariance of the self-reported data with just the original error that existed not in self-reporting, that should be 0, as we had that assumption before. So I rewrite X tilde here just as X plus the measurement error as well. I kind of have, the covariance here of X with the measurement error. If they're unrelated, this should be 0. But the covariance of the error term with itself, well, that'll always exist because those are the same variables. So here we've got the variance of the error term, and then that beta 1 would get pulled out front. And then if the X value is unrelated with the error, right, then now I don't have a covariance there. This is something kind of going back. I don't think we might have touched on it, but basically the variance of 2 components, if they're not related, is just the variance of each component added together. So all of this goes to say, right, if the measurement error is related, right, to the actual values of X, right, if that covariance is 0, I can rewrite my measure or my bias in that coefficient, right, and whatever the true coefficient is times the variance of the original X variable divided by the variance of that variable plus the variance of my measurement error. I am not going to make you walk through this step by step or reprove this, but this is essentially what leads us from point A. We have measurement error. The actual coefficient estimate we see, beta 1 hat, the estimate, will be the true effect times what? This fraction will always be what? I take something divided by itself, and variances are always going to be positive. Variances have to be positive, right? The very lowest variance we could have is no variation, which would be a variance of 0. So if there is no measurement error, the variance goes to 0. What is the coefficient estimate we see? This times 1, the actual effect. If we have any measurement error, the actual coefficient estimate we see will be the true estimate times something less than 1. Okay. So the estimate we see, if we have measurement error, will always be too small or closer to 0. So we would call this attenuation bias. It's attenuating that estimate towards 0. Doesn't matter if it's positive or negative, it's going to push that estimate to be closer to 0 or always underreporting the actual size of that coefficient. So, right? We're not going to walk through the step-by-step ever again, right? But the ultimate result we had is if we have classical measurement error where the measurement error doesn't depend on the values of X. So my alcohol example wasn't really a good one of this. Probably a better example of this would be if I asked all of you what your height is, are you going to get it exactly right out to the second decimal if you tell me? No. So you are technically giving me a value that has measurement error. Now, does that measurement error, is that correlated with your actual height? Probably not, right? I mean, you're going to be off a little bit either way. You're not intentionally lying to me. You know, it's likely you're trying to give me the right value, but you're going to be a little bit off if I actually take a tape measure and get your specific height, right? Maybe you could argue it's always going to be a little bit higher, right? But it's not that everyone reports a higher amount. It's that people who are taller would have to be reporting even higher amounts, or people who are shorter are reporting it. So maybe there's something there, but height is usually a good one. that people are going to try to give you the correct answer, but they're just going to be off by a little bit. There's no real relationship between how much they're off and what their actual height is, or that kind of covariance. If we go back, right, between the measurement error and the actual values, it's likely zero. People aren't lying to you in a specific way. It's just they're going to be a little bit off. So we would call that classical measurement error. So we just have some misreporting in the data. If we have classical measurement error, the estimate that we see will always be biased, and it's going to be biased towards zero, or what we call attenuation bias. Kind of like the unique thing here is this also kind of helps us prove that if we don't have measurement error, we're getting the correct result. Because I said, if we don't have measurement error, what does the variance of the error become? Zero, in which case the estimate we see would be the actual causal relationship times 1 would be right. Now, as that measurement error goes up, what's happening to our attenuation bias? So let's say that measurement error, we start to see like maybe people can get pretty close to their height. But if you ask me to report how many hours a year I watch TV, people are going to be wildly off, right? There's going to be a much wider range of measurement error. So if the variance of your measurement error increases, what's going to happen to the bias that you see? So this is where I think writing this out, sometimes I tell students this all the time, like writing things out, I think helps just kind of organize your thoughts. So if the coefficient estimate I see is the actual effect times the variance in that original X variable. And here ME is the measurement error. So I'll kind of write that as measurement error. If the measurement error in the variable you see is higher, what's going to be true about this fraction? If my denominator goes up, value of the fraction is going down. So my estimate is going to be even closer to 0, right? The attenuation bias is worse when I have measurement error that has a high variance. Any questions on that idea? Now, I probably wouldn't push you quite this far, but just to kind of start to think about these concepts. If the variance in the original variable is really high, right? So let's say I ask people what their income is. There's a pretty high variance on income. But if you try to report to me your income, you probably are going to like roughly estimate it. So even if I'm making $67,943, I know I probably make about $65,000, so I report that. So people are going to be misreporting data to you. But the measurement error, they're trying to get close. So that variance in the measurement error is going to be relatively small. So if the variance in income is relatively high compared to that measurement error, what would this what would this fraction be pretty close to? So think about if I have 100 over 100 plus 1. This is where putting hypothetical values can sometimes help us think about these things. This is going to be what? 100 over 101, or really close to 1. Whereas if the original variable has a low variance, same measurement error variance, what do I now have? I have what? 10 over 11. This is going to be much further away from 1, causing an even larger attenuation bias. So our attenuation bias, to be technical, it is impacted by the variance on the measurement error, but it's impacted more if that measurement error is of a relatively large size compared to the variance on the variable that you're looking at. So I probably wouldn't push you quite this far, but I might expect you to answer a question like this, right? If I have an increase or decrease in the variance of the measurement error, is that going to cause a higher or larger attenuation bias, or is that going to push me further away from kind of 0 or get me closer to 0? Any questions on this idea? All right. So one way we have to solve this, we'll talk about later on in this class, is instrumental variables. So this is kind of after thinking. So classical measurement error, we can actually put a sign and a size to what that attenuation bias would be. Non-classical measurement error, if the covariance of the actual X values is related to the measurement error. So this would be the idea that people who drink a lot are much more likely to give me a much lower value than people who don't drink a lot. They're more likely to give me the actual accurate value. The measurement error depends on the value of X there. Right? If that's the case, what we just talked about goes away, right? That it becomes a lot harder to actually identify what the bias will be. Now we know the bias will still exist. It's just that that bias is going to kind of be not necessarily attenuation bias, right? It could depend on how people over or underreport that X variable. So another example of this would be like self-reported intelligence. So this kind of works the exact opposite way. So let's say I was thinking about kind of a weird way to think about this, but like, here's somebody's actual intelligence, and I want to plot that against the measurement error. So people who are pretty intelligent, right, tend to actually think that they're not as smart as they are, right? Because they always, like, they realize, I always say it this way, you can now recognize what you don't know, right? So even if you're here, all of you might feel sometimes like you're not smart. You are smarter than a vast majority of the population just from the pure fact that you're in an econometrics course at Indiana University, right? That already puts you well above the average intelligence, right? But if I asked you how smart a lot of you feel, you're probably all going to underreport or give me a measurement error that's actually negative, right? You're going to underreport your actual intelligence. If my neighbor, God bless his soul, but his name is Billy, and I don't know Billy's actual intelligence. I don't think it's probably high. God damn it, he thinks he knows just about everything, right? So people of low actual intelligence are probably more likely to actually give me a self-reported intelligence that is higher, or their measurement error is actually going to be positive. So the fact that that measurement error has a relationship with the actual X value of intelligence, now I can't just know I'm going to have attenuation bias. I don't know which way the bias is going to be. It would depend on what directional relationship it is, and people are under or over reporting their, like in this case, intelligence. Whereas on my reverse example, it would probably, what's another one I could do? Basically, if we had another set of variables where instead the relationship looked like this, it would completely switch the sign of the bias, what direction that bias would be. So we're not guaranteed attenuation bias if the measurement error is in any way dependent on the values of X. Okay. So what's this going to look like? So, and here we're only talking for right now about measurement error in my independent or my X variable. Things will look a little bit different if there's measurement error in my dependent variable. We're going to hold off on that. I don't think we're definitely not going to get there today. Okay. So I just want to kind of go through and show you some examples, right? So we're going to use this life expectancy. I'm going to scale GDP just to make the coefficients easier to look at. So they're not like E to the bunch of decimals. So we're going to scale it by, looks like I did millions here. I'm then going to also go back to just using a linear relationship. So we get this nice coefficient that when BMI goes up by 1, GDP goes up by, on average 60, I think this was in millions, so 60 million, right? But this is my actual coefficient estimate. I'm going to try to prove to you what happens if we now have measurement error in self-reported BMI. Okay? So let's go down here and we kind of can think about, all right, I'm going to run this line that says set the seed at 1534. The reason I'm doing this is so we all have the same values. We're going to start to use this kind of function in Stata, which is it can create random numbers for us. The problem is, if they're random numbers, when you run the code, you might get a different set of random numbers. And so we'd all be looking at slightly different values, right? So there's a secret to make sure it starts out with the same random numbers. Now they're still random, it would just be the same set of random numbers for all of us. That's what that set C does. You don't have to worry about this for a problem set or anything like that. It's just for the sake of kind of instructional use here in class. So I'm going to generate some measurement error in my BMI. I'm going to use a uniform distribution, and I want that measurement error to be a random number somewhere between 1 and -1. So it's just going to start to generate different random measurement error for every single observation of my data set. So creating this new measurement error variable just randomly from this uniform distribution. I could use a normal distribution if I wanted. I just chose the uniform to start out here. And we'll get looks at a normal distribution later on. So if I run this line of code and I look at the data, what I've now done is created this measurement error variable where it's somewhere between 1 and -1, right? And it's just random. So this would be classical measurement error. Doesn't depend on the value of BMI. It's just random, okay? So what I'm then going to do is create this new BMI variable, which includes the actual BMI, but also adds in the measurement error. So the thought experiment is, what if I had the data and it was only self-reported BMI? So I only have the data that has the measurement error built in. I can't like identify what it is. It's built into that BMI variable. So now if I run the regression of GDP on BMI, but I'm using the BMI that includes that measurement error, we know the original coefficient should be 60,088, right? But if I have a variable that has measurement error in it, anytime I have measurement error, the variance is now going to be something other than 0. We said if it's classical, we could use that equation. So as the variance of the measurement error goes up, we had attenuation bias, or the estimate we see is going to be a little bit smaller. We can prove ourselves. We improve this to ourselves with data. So when I run this regression, I should see something lower than that 60,088. Sure enough, I get about 54,000. I have attenuation bias. The estimate I see is going to be a little bit too low. Okay. Any questions on this idea before we keep moving? Anything I've done here kind of in this do file? Okay, so now this kind of goes along with what we were looking at before. If I have now, let's call this a second random measurement error, but now instead of being between 1 and -1, it's random numbers between 10 and -10. What's going to happen to the variance of my measurement error? It's going to be larger, right? So when we go back, it's the same thought experiment as we did earlier. If the measurement error is now larger, the variance on the measurement error, the estimate I see is actually going to be even lower. So when we had the variance of the uniform distribution, right? Our original variance, right, caused the estimate to fall to about 54,000. If I have an even higher variance on my measurement error, this new measurement error, bigger variance, I should see an estimate that's even lower. So if I now create this new measurement error, I create BMI that includes this larger measurement error. Now when I run the regression, what estimate do I see? It's really been attenuated. It's gotten a lot closer to 0. Okay. So when we have really large measurement error, we might look at this and now notice what's even happened to the statistical significance. When I had a small measurement error, okay, well, my test statistic is a little bit small, but my p-value is still 0, I'd still be making the same rejection decisions. But as the measurement error goes up, if we think about how do I determine my p-value, it's based off of my what? A statistic. Test statistic. So if I get my test statistic by dividing that coefficient by the standard error, if we know that this is going to be closer to 0, right? We have attenuation bias. What's going to happen to our test statistic? It also is going to be closer to 0, which means if my test statistic goes down, what happens to the area to the right of it? Larger. So my p-value is going to actually be higher. It's less likely I'll find statistical significance as well. So the larger that measurement error variance gets, not only will I see a smaller size on my coefficient, I could lose statistical significance. And this is like a good example where when I originally had that small measurement error, I didn't lose my statistical significance. Now I lost some. My test statistic went from what? 5.1 to 4.7. When I had really high measurement error, my coefficient was a lot smaller, and I now didn't quite lose it at all levels, but now I can't say it's statistically significant at the 99 or 95% level. Now, if I wanted to extend this thought experiment, let's just say, I'm going to copy this, paste it, all this measurement error, big 2, measurement error, big error 2, right? And instead of negative 100 or negative 10 to 10, I'm going to go negative 100 to 100. Well, now when I rerun this regression, with my even larger measurement error, my coefficient should be even closer to 0. Wider, or the larger that variance on my measurement error, the closer that attenuation bias is going to get me to 0. It's likely now, if I'm losing statistical significance, well, if I go from 1 to 10, we kind of lost 99 and 95% statistical significance. When I go to 100 and negative 100, it's likely I'm going to lose all. So if I run this regression with really high measurement error, I don't see 7,000 as my coefficient. I get 51, right? It's getting a lot closer to 0. And what has happened to my statistical significance? It is way gone, right? I'm at a p-value of 0.9 now. So when we have this even classical measurement error, it's going to decrease the size of our coefficient, which inherently lowers our test statistic, increases our p-value, making it less likely we find statistical significance as well. So we had measurement error and we didn't know it. We might ignore this result. We might say there's no relationship between these two variables. Well, in fact, if we had the actual BMI, the accurate instead of the self-reported values, it's highly statistically significant, and the coefficient is much larger than what we saw if our data included this huge measurement error. Hopefully we can kind of see like why it matters that we have measurement error, because we're going to get incorrect results, right? This will be a threat to internal validity because we now don't have a statistically significant result when we in fact should. Okay. Any questions over anything here? Okay. Oh, let me think about what I want to do next. So we have 20 minutes. Maybe I'll do this. We'll do this. We're using the same kind of idea, and so I want to touch on this. If we have time, we'll kind of go to non-classical measurement error, just to kind of even further prove this to you and kind of show you the capabilities we have in Stata. Right? So I'm going to instead pull up in the other do file for the week, which was data issues Monte Carlo F25. Okay, so I'm going to go make sure got my global path set correct there, since I think I was running this off of my personal device instead of my OneDrive. I'm then going to open up that life expectancy data, scale GDP, just to make that coefficient easier to look at. And then we're going to run that same regression of BMI, right? Trying to predict GDP. We get that 60,088. That's the actual coefficient, what it should be. What I'm going to do here is first, I'm going to save what the actual coefficient is. So that's that BMI coefficient. I ran the regression. We can start to use this underscore B. It's just going to save that BMI coefficient. So that's just so that I had it, so I can go back and refer to it and use it later on. But I basically just stored that value in every observation, right? Just so I have it for later on. I'm also going to summarize that BMI variable, and I'm going to save its variance, because that was one of the other things. Did I lose my internet connection here? Possibly. It's gonna get upset. Let's see. Well, maybe we'll be limited here. There we go. All right, a little bit slow. So I'm going to summarize the BMI variable and then just keep its variance as well. Because if we're going back to thinking about that attenuation bias that we had, we said it'll be the actual effect times the variance in our X variable, which is now BMI, divided by the variance in BMI plus that variance in our measurement error. Okay, so I just kind of saved this value and I saved this value. I know what those are. The thought experiment I'm now going to do in Stata, right, is go through and say, okay, what should, if I run this regression with measurement error in my BMI that is equal to a variance, has a variance equal to 1, right? Then what should that coefficient I see be? Well, if I know that this is 60,088, now I already forget what was the variance. It was something like 4.81 was the value that Stata told me I saved. And I now know the variance on my measurement error is 1. I can actually calculate the coefficient estimate I will see if I run a regression of GDP equal to BMI with BMI that has measurement error of a variance of 1. So I can do this math. I'm just going to have Stata do the math for me by using that display command. Take the actual coefficient, which was 60,000, divided by the BMI variance of 4.8, out to quite a few decimals, and then add in that measurement error variance of 1. So the estimate I should see, if I run this regression with a BMI variable that has that measurement error variance of 1, instead of seeing 60,000, I should see just under 50,000 here. So what I'm going to do, instead of using that set seed, you can actually create programs in Stata. So I'm going to create this program, and it basically will run this kind of line of code. Oh, where do I want it? Here you go. All right. Where it's going to go through, open up that life expectancy data, scale the GDP variable like we did. It's going to create random measurement error. I'm now going to create the random measurement error not from a uniform, but simply from a normal distribution, just to show you that it doesn't matter what distribution measurement error comes from. Now, I set this to be a standard normal, right? 0 mean, variance of 1. So I know the variance has a variance of 1, which is what I originally had set up, right? And then I'm going to create this new BMI variable, which is the original BMI plus the measurement error, run the regression with the variable that includes the measurement error. I'm going to do this 100 different times. So I created this program called MyReg. Stata is going to run it 100 times. Every single time, it's going to generate a new set of random numbers. So I'm going to have 100 different regressions with different random numbers for my measurement error. And then I'm going to take the average of those coefficients, the averages of those standard errors to see, okay, on average with this measurement error, what estimate was I getting? The value I should see was what? 49,752. So hopefully when I run this code and I run this program 100 different times, I then look at the average coefficient I'm seeing. Because it is including that measurement error, I should know that I see this 49,752. So I'm going to go ahead and run this. It might take a second, right? But okay, I'm a little bit off, right? I said we should be seeing what, like 49,700 something? I'm close, but it's a little bit off. Why? Because technically to prove this, I would actually have to randomly generate numbers how many times? Not 100, but infinite number of times. I can't really do that. But if I do it instead of 100, let's say I run this 1,000 times, I should get a value that's a lot closer, right? So I'm going to do this 1,000 times. This is where I'm always worried I'm going to break the computer. It looks like here we've at least got good enough Wi-Fi where it's running this off of Stata. See, it takes a while to do this 1,000 different times, but when we look at the average across these 1,000 different random sets of numbers, what do we end up with? Something that's a lot closer to that 49,752. And if I did this for 10,000, it's going to be even closer, right? So I can always prove to myself that this is the actual equation that would work. I just have to kind of make sure I have that rep set pretty high. Okay. Now, let's say everything is exactly kind of the same. I'm going to scroll down here to this second regression. I'm doing the exact same thing. I'm going to do this 1,000 different times, 1,000 different sets of random numbers, right, to create my measurement error. But now my measurement error is coming from a distribution that's normal and has a mean of 0. And I believe this is setting the standard deviation. So the standard deviation would be 10, which means my variance would be 100. So it's going to have a much higher variance. So what should happen to the coefficient estimate I see? It should be a lot. So if the measurement error has a much higher variance, we said the attenuation bias is going to push it closer to 0. Right? So if I run this, right, with a much higher variance on that measurement error, the average estimate I should see across these 1,000 different random sets of numbers to generate this measurement error should be much smaller than that 49,000. In fact, now it's all the way down at 2,800. Right? So we can kind of prove these kind of concepts to ourselves by running these simulations in Stata. And in fact, if I kind of wanted to, I could do a very similar sort of thought experiment where I take the actual coefficient. I've got the variance on the BMI variable. It's just now the variance on that distribution I was pulling from wasn't 1, it was 100. Sure enough, I should be seeing an estimate right around 2,700. I'm seeing 2,800 once again. It's going to be a little bit off. Technically, to kind of get this, I'd have to run this like 10,000 times, and that's just going to take a while, right? But this is like the power of what we can start to do in Stata. You can create these programs and run these what we call Monte Carlo simulations. So they use these a lot in other econ courses. When we have like the idea of what our model should look like, and we want to run a prediction for a bunch of sets of random numbers, right? We do a very similar thing. Okay. So that I think is about what I want to get at here. So I think next class we'll talk about measurement error and the dependent variable. So we'll kind of stop here today, this Monte Carlo simulation file or Monte Carlo data issues file. Let me think if there's anything else. I've got 10 minutes. So what can we kind of grab onto here? Oh, I'll introduce this idea just to kind of prove something so that we've kind of already talked about. So we said this idea of classical measurement error. We knew the estimate we see is going to be closer to 0. We're thinking about measurement error that depended on the X value, kind of like that self-reported intelligence idea. All bets are off of what's going to happen to our coefficient. So what's an easy way of thinking about this? Excuse me. So I'm going to go back up here. I'm going to run or open that life expectancy data, scale my GDP variable. And I'm going to set that seed so we're working with the same set of random numbers. And then I'm going to come down here to non-classical measurement error. So I'm now going to create some measurement error. That notice the measurement error. Oh, we have to run that code. Where is it at? Measurement error was from a uniform distribution. So my new measurement error will be some random number, but then it's also going to be a function of BMI. So the measurement error will now depend on the values of BMI, just like our measurement error and self-reported intelligence depended on how actually intelligent I was, right? So if I have non-classical measurement error, I kind of build that into my BMI variable. Now, when we run that regression, I don't necessarily have attenuation bias. I could see estimates that are higher or lower than that original value of what, 60,088, I think was what we had. So sure enough, if I run this, I get about 49,000. So it's here going to be lower. But notice if I do a similar thing, but now the measurement error is not positively related to the values of X, it is now negatively related. So the idea here would be as BMI went up, people were more likely to kind of underreport their BMI. Now, if I have the flip, whereas BMI goes up, people are more likely to actually overreport it. My estimate on that coefficient is going to be wildly different, right? So if I now have this, instead of seeing 49,000, my coefficient estimate, oops, I forgot to select the line of code, which is actually run the regression. Now I see an estimate that is actually greater than what the true estimate should be. So when I have non-classical measurement error, I'm not guaranteed I'm going to see a smaller size coefficient. It could be larger, could be smaller. It all depends on what is that relationship between the measurement error and the actual values of that X variable. So the simplest way to kind of show that is if the measurement error is a positive function of the X variable, we end up with an estimate that was too low. And if the measurement error is a negative function of the actual values for that X variable, we end up with a coefficient that is too high. Okay? And what I'm more kind of wanting you to focus on there is that if we just have non-classical measurement error, not to remember like, is it higher or lower, just that we don't know which direction it's going to go. Okay? Because here I can create what the relationship is. In practice, I have no idea what that function looks like between the actual X values and the measurement error. But if I think that it might be non-classical, right, that there is some relationship between those, my coefficient could be higher or it could be lower. I use that measurement error variable. Questions on that? And then, it just gets even more complicated. So here I created one. The measurement error, it's not just I add or subtract a value in, it's multiplied by the value of BMI. You could do a similar thing there. What we end up seeing is, well, the estimate is smaller and quite a bit smaller. So this estimate could go all over the place. Just depends on what that functional form looks like between the measurement error and the actual values of that X variable. But if we had classical measurement error, that's the one where we can actually determine what the true effect is, right? Where we actually know what that attenuation bias would be. And it was some function of the variance in that X variable to the variance of the measurement error. You might see questions like that pop up where you need to be using this equation if we have classical measurement error. And I should be more specific. All we've talked about today is measurement error in our X or our independent variable. Next class, we'll talk more about what happens now if we have measurement error in our dependent or our Y variable. And that looks a little bit different. So classical measurement error, it's not ideal, but we can actually put a sign to it. We know that it's going to push my estimates closer to zero, which in some ways is good, because if I know that if I find a statistically significant effect with a variable that has measurement error in it, if I didn't have the measurement error, what would definitely be true? It's going to be even greater in size, and my statistical significance would be even larger as well, right? So it sucks that I have measurement error in this variable, but if I find a statistically significant effect, well, then I can guarantee it's statistically significant if I had the actual values. Now, if it's non-classical measurement error, all bets are off. I have no idea what the true effect between those two variables are. Any questions over anything set up to this point here? So here's where I'll leave you with one piece of advice. So kind of just to identify, we probably won't waste time on this here. We'll start class 2 with measurement error in the dependent variable. I'm saving these to my OneDrive, so we'll kind of start where we left off on Thursday. I didn't use an in-class quiz today, which likely means I'll probably use one next class, right? So you showing up today isn't completely valueless, so you know that you only should be showing up Thursday. I also want to say one more thing. So we're starting to dive into some things that are a lot more discussion-based, and I'm trying to kind of show you some things that might even be outside the scope of this class. I will do my best to mention what those things are. I think once you start to look at those practice problems, it'll be kind of easier to identify like what the expectations of you based off of. Usually the slides kind of help do that as well. You won't find in the slides where I'm giving you any of like these functional form stuff. Yeah, it wasn't the do files. But I do want to show you kind of what the next level would be if you're thinking about taking kind of the next level of econometrics course and this type of issues that we'll start to run into. So kind of the end of this class, we're going to still work on adding some tools to our tool belt. But I'll also start to mention some like additional tools that would exist after you would leave this class that would see at the next level. I also just, as a sure I'm talking to the wrong population here. Maybe my external validity is not great. But as I'm looking at some of these problem sets, I'm not an idiot. And I know that some of you out there are probably trying to use AI to generate some problem sets. I'm just telling you right now, it's doing a piss poor job of it. I mean, when I'm seeing code that looks probably more complex than even something I would write, I know that you're probably not. I mean, maybe I'm underestimating some of you. Maybe you could. But when you're talking and you're using models outside the scope of anything that we would ever talk about in this class and is more complicated than we've touched on in class, maybe you did the extra work and you're interested. You're doing it and you're still doing it wrong. Probably lets me know you're using AI and it's not doing a good job. You're losing a lot of points. So the couple that I did grade, I looked through them and man, I mean, it's like getting like 2/3 of the problems correct. Like that's not going to do very well for your grade, right? So take some time on these. Like they're going to be valuable for you to learn how to code, right? Especially if you are thinking about getting a job once you leave here. You're not going to be able to use AI when you work. I mean, you'll probably hopefully if you develop the skills now to understand how to do the coding basics, you can then understand how to use AI to be an even more efficient coder for you and identify where it's getting things wrong. If you're just simply trying to rely on it now, you're not building a valuable skill that you should have thinking about kind of entering that workforce. So that's just my 2 cents, what I'm noticing. Relying too much on AI, it's not going to bode very well for your grade, at least at the level it's at now. Get back to me in 5 years, maybe I have a different opinion. I don't know. But at least at the level they're at now, it's not doing a very good job at kind of producing good results for these problems. Okay. And this is also where if you have questions, someone emailed me yesterday. We're going to problem set 5 and you have questions. You're not exactly sure if this I'll take a look at your code. You can always stop by office hours and ask me before the assignment is due. You can always send me an email to say, is there an agree? I'm not really sure if I'm doing this correct. Can you look over it for me real quick? I'm not going to look over like your entire due file, but I have very specific questions. I'm always open to kind of answering those prior to the due date. Okay. So that next problem set due at the end of next week on Wednesday. Please start working on that early, get those questions out of the way, get as many points possible there. And then we'll pick up on these data issues next class. Okay. All right. See you on Thursday.